hyperbolic geometry is quite common in some types of geometric study and quite uncommon in algorithmic computational geometry. And so this is sort of partly an exploration of why that is, and partly a survey of what few results I know of that are both hyperbolic and algorithmic. So let me start. Just give you a brief overview of what hyperbolic geometry is and what some of its properties are. This starts with, in the 19th century and earlier, mathematicians were interested in the Euclidean axioms for geometry. Of course, as Hilbert went through very carefully, and these aren't really exactly what you need to define geometry because they depend on properties that are assumed about what it means to be a line and a point that need to be defined more precisely. But Euclid had these 5 axioms for Euclidean geometry, and the first 4 were relatively straightforward, and everyone was concerned that the 5th one didn't seem to fit. So Bolyai's name should probably be on here somewhere too, but Lobachevsky suggested that somehow a space of constant negative curvature, in modern terminology, a Riemannian metric, where every point is symmetric to every other point, every direction from every point looks the same as every other point, but unlike the normal Euclidean space, the intrinsic curvature of the space is negative, would somehow supply a geometry that has a different replacement axiom for the 5th axiom. The 5th axiom in Euclidean geometry is that for any point and every line where the point is not on the line, there's a unique parallel line through that point. And what ends up happening in hyperbolic geometry in these spaces is that instead one has infinitely many parallel lines that don't ever meet the line you started with. Also in the 19th century, Klein suggested that geometries could be defined on by their symmetries rather than by their metrics, and there's a way of doing that for hyperbolic geometry. This doesn't really say so much what it is, but what its properties are. There are ways of defining hyperbolic geometry, and we'll get to that in a few slides, as sets of Euclidean points with different definitions of what a distance is and what a symmetry is. And that gives you a way of understanding hyperbolic geometry extrinsically as it relates to Euclidean geometry, but it can be defined intrinsically by these means as well. Different people have tried to look at what hyperbolic geometry would look like. The most famous of them is, of course, Escher. So this is one of several of Escher pictures that purports to illustrate the hyperbolic plane. Actually, I'm not sure that Escher claimed any such thing, but has been purported by others to illustrate the hyperbolic plane. Actually, if you look at this picture, it's a little strange. It seems to be squares and triangles that they shouldn't meet up this way. And the problem is, if you think that these white arcs are hyperbolic lines, it doesn't work. That this doesn't actually match up with the way hyperbolic geometry behaves. The angles of the triangles and the squares don't behave the way they should at the vertices. The actual hyperbolic lines in this figure are not the white arcs, but oops, that wasn't what I wanted. Here we go. They're arcs passing through the centers of the squares. Okay, here's another picture of the hyperbolic plane. There's this lovely video, Not, that came out over a dozen years ago from the Geometry Center that tried very hard and I think did a great job of portraying what it would be like to be in hyperbolic space from the inside. And this is a still from that video. So if you really want to get a better visual intuition of what hyperbolic space is, I would recommend you just go look at that video several times. Hyperbolic space has several unusual properties. Here's just one slide of them. In Euclidean space, if you have any triangle, you can surround it by a circle. If you have any circle, you can surround it by a triangle. So there's not really any difference in area or other properties like that between circles and triangles. In hyperbolic space, it turns out that triangles have at most constant area. The area of a triangle is actually, well, in Euclidean space, the sum of the interior angles of a triangle is always exactly pi. In a hyperbolic space, that sum is less than pi, and the area of the triangle is the amount by which it is less than pi. This is known as the Gauss-Bonnet theorem. And in particular, there's a special class of triangles where all the vertices have been stretched out to at infinity, and being at infinity, they have zero angle and area equal to pi. And that's the maximum that any triangle area can be. On the other hand, it's easy to have a large area circle. One can define, just like in Euclidean space, a circle around any point with a given radius. And the area turns out to be exponential in the circle radius. And also, unlike Euclidean geometry, the areas and circumferences are proportional to each other. In fact, the area over the circumference is always strictly less than 1, where the limit goes to 1 as the radius becomes large. So one can have circles that are much bigger than any triangle. A little counterintuitive. Okay, so let's start talking about algorithms. And to do that, I need to talk about how to model hyperbolic geometry in Euclidean geometry. And this section is sort of a good news, bad news section. It turns out, even though there haven't been many papers on algorithms in hyperbolic geometry, there are a lot of algorithms that one can find more or less directly from their Euclidean counterparts. So that's good news. There's lots of things we can compute. The bad news is it's all very easy. So we can't publish anything about it. But there are several ways of modeling hyperbolic space, and the two that I want to look at are called the Klein model and the Poincare model. So these are somehow combinatorial representations of hyperbolic space within Euclidean space. And obviously, since those two spaces are not the same, you're going to lose something. There's going to be something distorted. But in both of these models, one ends up with points in hyperbolic space being represented as points in the unit disk in Euclidean space. And then the lines of hyperbolic space are represented as some kind of object in the unit disk. So in the Klein model, we model points in hyperbolic space as points in the unit disk. We model hyperbolic lines as chords of the unit disk. And it turns out that the hyperbolic space can be mapped to the unit disk in such a way that all of the lines are nice straight chords. But this map distorts many other properties such as areas and angles and anything else that you might want to measure. All it preserves is the straightness of these lines. So the point line incidence is preserved by this transformation. And I'll go over this in a little more detail in the next couple of slides. The Poincare model is very similar. We can map the points to points in the unit disk, but now hyperbolic lines are mapped to arcs of circles, and specifically of circles that meet the boundary of the unit disk at right angles. So the problem with those white arcs in the Escher picture is that they don't meet the boundary at right angles. They meet at some other angle. And you can go from one of these representations to the other by using polar coordinates and just using the appropriate function to map the distance from the center of the circle in this representation to the distance in this representation. All the combinatorial properties are preserved so that you see in these two hyperbolic line arrangements, they meet in the same sets of points. You have triples of them meeting in a point over here exactly when you have a triple of them meeting in a point over here, etc. I should mention, by the way, there's also something that is called the Poincare model. That's almost the same as this, where instead of the unit disk, we take a half plane, or in higher dimensions, a half space, and model hyperbolic lines again by circular arcs that meet the boundary of the half space perpendicularly. I don't know of a similar corresponding thing for the Klein model. Obviously, if you had a chord that met the boundary of a half space, it would just lie on that boundary and not protrude into the inside, and it wouldn't work as well. So that half space model only works with the Poincare type of model as far as I know. And all of this generalizes to higher dimensions in a very straightforward way. So in the Klein model, the one where hyperbolic lines correspond to chords in the unit disk, straight objects in hyperbolic space are mapped to correspond to objects that are also straight in the Klein model of the hyperbolic space, which lives in Euclidean space. And convex objects in hyperbolic space correspond to objects that are convex in the Euclidean space that models it, and vice versa. But as I said, distances and angles and so on can't be read off so directly from that model. But what this means is that anytime you have an algorithm that only uses these two properties, straightness and convexity, one can immediately use that algorithm in hyperbolic space by mapping the hyperbolic space to Euclidean space with the Klein model and then applying the algorithm. So we can compute convex holes in hyperbolic space in the same time that we can compute them in Euclidean space, and they have the same combinatorial properties. We can compute hyperplane arrangements. We can triangulate polygons. We can use these various simplex range searching data structures, epsilon cuttings, spanning trees with low stabbing number. All of these things just depend on these combinatorial properties. And so they immediately work. And we get lots of nice algorithms. There's also, by the way, I pulled this formula from the nice book by Hilbert and Cohn-Vossen, Geometry in the Imagination. Has a little bit of section on hyperbolic geometry. And one of the things it points out is that the Klein model has a very nice distance formula in it. I'm not going to spend a lot of time on distance and angle and formulas in hyperbolic geometry, but in the Klein model, if you want to measure the distance between B and C, one can extend the line segment between those 2 points into a line that meets the boundary of the hyperbolic model at these points at infinity on the boundary, and then just take a log of a cross ratio, and that gives you the distance. Okay, so the Poincare model is a little different. It doesn't preserve convexity. Something that looks convex in the hyperbolic space might be mapped to an object that's not convex in the Poincare model. For instance, a line segment. A line segment is a convex set in hyperbolic space, but is mapped to a circular arc, which doesn't look very convex. On the other hand, circles and spheres in hyperbolic space are mapped to circles and spheres in the model. This is not really a vice versa relation. Some circles and spheres in the Poincare model correspond to circles and spheres in hyperbolic space, namely the ones that are entirely contained in the unit disk. Then we also have the circles in Euclidean space that meet the boundary of the disk perpendicularly, and those correspond to hyperbolic lines. There's also two other kinds of things in hyperbolic space that correspond to Euclidean circles. One of them is a circle that meets the boundary of the Poincare model tangentially. And that corresponds to something called a horocycle. And the other is a circle that meets the boundary of the Poincare model in two places, like most circles would, but that does so at an angle different from 90 degrees, and that's called a hypercycle. So there are these four types of objects that correspond to circles. The Poincare model also has this very nice property of conformality. That means that if you have any two curves in hyperbolic space that meet at an angle, which can be defined in an appropriate way intrinsically to the hyperbolic space from the Riemannian metric, then the angle that they meet at is the same as the angle that the models of those curves meet in the Poincare model. So one can immediately read off angles between objects from the Poincare model of hyperbolic space. But as I said, straightness and convexity are not preserved. Distance, one can compute using an appropriate distance formula different from the Klein model distance formula, but it's not the same as Euclidean distance, obviously. And so one has to be careful what one does. But any computational geometry algorithm or property that depends only on circularity then can be made to work in hyperbolic space. And the most important of those, I guess, would be the Delaunay triangulation. Because the Delaunay triangulation is defined by this property. It consists of the triangles, the circumcircles of which are empty of other points. 3 points in the Delaunay triangulation are connected in a triangle if and only if the circle through those 3 points doesn't contain any fourth point. And that property is a property that only depends on circularity and containment, and those properties are preserved by the Poincare model. The Delaunay triangulation in 2 dimensions is useful, among other things, for computing minimum spanning trees. The minimum spanning tree is always a spanning tree of the Delaunay triangulation, and so one can compute the minimum spanning tree in Euclidean space efficiently in n log n time by computing the Delaunay triangulation using any of many known Delaunay triangulation algorithms. This is a planar graph with n vertices and edges. One can then apply any reasonably efficient graph minimum spanning tree algorithm to get the minimum spanning tree of that graph, and that's the Euclidean minimum spanning tree. That same construction, substituting the hyperbolic distance for the Euclidean distance in the graph computation, immediately works for hyperbolic space. And we have bounds on combinatorial bounds or algorithms on numbers of incidences between points and spheres. That works. Alpha shapes are some kind of graded subcomplex of the Delaunay triangulation. And the grading is usually defined on a parameter alpha, which tells you the radius of which circumcircles to keep. But that part works just as well hyperbolically as Euclideanly, and so on. So again, we get lots of algorithms and different ones from the ones we get from the Klein model. Okay, so what I wanted to do for the rest of this talk is to go through what I know about algorithms that are not quite so trivial, that somehow involve hyperbolic geometry. Of course, because of the existence of these models, it's possible to describe any algorithm that bases itself on hyperbolic geometry using only Euclidean terms. So it's a little hard to define what it means to be a hyperbolic geometry algorithm, but I think it'll be clear from these 2 examples. And these are the only 2 examples of algorithms or algorithm papers I know of that involve hyperbolic geometry in a less trivial way than just applying the model and then using a Euclidean algorithm. So the first one comes from this nice paper by Boissonnat and some of his co-authors, and the references later. The problem is to construct, and both of these problems that I'm looking at in the rest of the talk concern actually Euclidean problems. What I want to do is define somehow in the Euclidean space, but hyperbolic geometry comes up somewhere in the solution. And so here the problem is just 3D Delaunay triangulation construction. The 3D Delaunay triangulation, again, we have tetrahedra such that the sphere through the 4 vertices of the tetrahedron does not contain any other sphere. And that, what? Any other point, right, of the input set. And that collection of tetrahedra with a suitable general position assumption forms a partition of the convex hull of the points into tetrahedra. It's dual to the Voronoi diagram, which is a partition of space into cells, where the cell of a point is the set of other points in space that are nearer to that input point than to any other input point. And here I found this nice picture on the web of, I mean, it's hard to draw these complex three-dimensional objects in such a way that you really get a feel for it as three-dimensional, and I think this picture succeeded. So the blue pipes in this picture represent the edges where three Voronoi cells meet. So they're the boundary, the one skeletons of the Voronoi cells. And the green edges represent the edges of the Delaunay tetrahedra of this point set. Okay. In 3D, this is closely related to what Gil talked about last talk on neighborly polytopes. In 3D, it's possible to have a Delaunay triangulation where the number of edges or the number of tetrahedra is quadratic in the number of input points. And it's not hard to come up with algorithms where the running time is at most quadratic in the number of input points. But for most point sets that come up naturally, the anecdotal evidence, at least, is that these Delaunay tetrahedral triangulations are not as complicated as that. There's been some work by Boissonnas and Erickson and others on actually bounding the size of the Delaunay triangulation based on some assumptions about how these points behave nicely. That the points leading to quadratic-sized Delaunay triangulation sets, these point sets are very special and don't tend to actually come up in practice. So what we would like is an algorithm that computes this triangulation in time that's roughly linear in the size of the input plus the size of the output. So that if the size of the output is quadratic, we're not wasting too much extra time computing the output, but when the size of the output is closer to linear, we get a time bound that's closer to linear. And that can be done. There was this nice paper by Chan, Snoyek, and Yap that is output sensitive with only this extra log squared factor in the running time. But what we would like is to do even better than that, or to make it simple enough that we could use. And so that's what I want to talk about. A paper by Boissonnas, I don't know how to pronounce all of these authors' names, Carezzo, Devilliers, and Théot, on output-sensitive Delaunay triangulation for a special case. The special case that they consider is point sets where some of the points are on one plane in space and some of the points are on another plane in space. So there's only these two planes that together define a point set, and we'd like to find the Delaunay triangulation. This turns out to be an easier special case than the more general case. Okay, so this slide, there's nothing hyperbolic on it. There's sort of two cases to their algorithm, and this is the easier of the two cases when the two planes that contain the points that you're interested in are parallel to each other. So we would like to find the Delaunay tetrahedra, or equivalently the Delaunay spheres of these point sets. And what we can do is think about how that sphere might intersect the planes containing the 2 points. And of course, the intersection of a sphere with a plane is just a circle. So this Delaunay sphere that we're hoping to find is going to intersect each of the 2 planes in a circle. And because this sphere is a Delaunay sphere, it's going to have 4 of our input points on it. And of course, those points, because they're on the planes, are going to be on one of the circles or the other. So there might be 1 input point on one circle and 3 on the other, or they might be split 2 and 2. Now, if we look within each of these planes, the points that are within that plane themselves define a Delaunay triangulation, or dually a Voronoi diagram. And I've only drawn the dual here with these dotted green lines. And also, in these planes, these circles that this empty sphere is intersecting the planes in are going to continue to be empty. So they're going to, if you look at the center of an empty circle, the feature of the Voronoi diagram that that center lies on tells you how many points are on the circle. Right? If you have a circle that's empty in its interior and has one point on the boundary, then the center of that circle has to lie in the interior of a Voronoi cell. If we have a circle that has 3 or more points on its boundary and is empty in the interior, then the center of that circle has to lie on a Voronoi vertex. And if we overlay these two planes on top of each other, just perpendicularly in 3 space, what we end up is this center is in a Voronoi cell, this center is at a Voronoi vertex, and we get a vertex of the overlaid diagram formed by a vertex that's in one diagram contained in a cell of the other. If the points are split 2 and 2, if we have an empty circle on one plane that has 2 points on its boundary, then the center of that circle is equally distant from both points and is therefore on the edge of the Voronoi diagram. And the center in the other plane is on a different edge of the Voronoi diagram because it also has 2 points on it. So when we overlay these two diagrams, this edge is going to cross this edge at that center point. And the converse is true. So we can read off all of the features of the 3D Delaunay triangulation by computing two-dimensional Voronoi diagrams, one in each plane, overlaying these two diagrams, placing them on top of each other and constructing the resulting arrangement of line segments. There are efficient algorithms known for doing that. And then whenever we have a vertex of one arrangement that's contained in a cell of the other, we construct a Delaunay tetrahedron with these 3 points and this point. Whenever we have two edges, one from one diagram, one from the other, that cross each other, we construct a Delaunay tetrahedron that has 2 points on one, 2 points on the other. And those are all the Delaunay tetrahedra of this 3-dimensional point set. So this simple 2-dimensional construction lets you construct 3D Delaunay tetrahedralizations. Okay. Now the more complicated case, and this is where hyperbolic geometry comes in, is what happens if the points are again on 2 planes, but the 2 planes are not parallel. Well, instead of projecting perpendicularly the planes onto each other, the obvious thing to do, any 2 planes that are not parallel meet in a line. And one could try to rotate one plane into the other, like the pages of a book or magazine rotate on the spine until they touch each other, and use that as our way of overlaying 2 diagrams. And if one tries to do that using Euclidean Voronoi diagrams, it turns out not to work. And the reason is a little subtle, but if we go back to this picture, there's sort of a few things that I didn't say about these spheres and circles and how they relate to each other. If I take these 2 parallel planes and the Delaunay sphere that intersects them, not only do I get a circle in one plane and a circle in another plane, but when I overlay those 2 circles perpendicularly to the 2 planes, these 2 circles are concentric. The 2 centers are in the same place, and so it makes sense to talk about which feature of the Voronoi diagram in this plane contains the center and which feature contains the center over here, and overlay those 2 features. If I try in Euclidean space rotating 2 planes into each other through their common line, and those 2 planes have circles on them that are defined by their intersection with a common 3-dimensional sphere, those 2 circles will not in general be concentric. And so you can define these circles. You can look at the Voronoi features that they correspond to, but those Voronoi features might not intersect each other in the way that you hope. So for points that are not on parallel planes, if they're split this way and this way, the center, the Voronoi vertex here that corresponds to this triple of points might not actually lie in the cell that you want it to. And in this case, the two edges might not cross the way you want them to. And so you can't just overlay these diagrams and read off what happens. And then the solution turns out to be to view these planes, or more precisely the half planes bounded by the intersection line of the planes, view them as hyperbolic planes rather than Euclidean planes, and compute a hyperbolic Voronoi diagram. And if you think about actually forming a three-dimensional model of hyperbolic space that has this intersection line on its boundary, when you rotate one plane into each other around this line at infinity, the arc that any point travels through is a piece of a circular arc that is perpendicular to the boundary. So it's a hyperbolic line. The center of one point rotates along a hyperbolic line that's perpendicular to that plane that you're rotating. And so these circles end up being concentric and everything works. And the result is that we get this very efficient, very simple way of doing Delaunay triangulation of points on two planes, even when the two planes are not parallel.
So the motion is a Euclidean rotation then, of the planes?
Yeah, you could describe it as a hyperbolic motion, but it's not a rotation. Because, well, I mean, it's not a rotation around a hyperbolic line because this line is at infinity. So it's easier to think of it as a Euclidean rotation, yeah. Okay, any questions on that algorithm before I move on?
For points in two half planes, or what do you do if there are points on
Well, if there are points on both sides, I'm not really sure what happens near the middle. I mean, you could treat two halves overlaid and two other halves overlaid, and then maybe you have to overlay them in pairs and other pairs. It's probably easiest just to think of this as points in two half planes rather than points in two planes, but I think it can be generalized.
Could you instead do the projected transformation and move the line to Euclidean infinity? Don't preserve spheres.
Yeah, what he said. I mean, that's sort of what we're doing. I mean, in some sense, parallel planes are planes that meet in a line at infinity, and we're rotating around that line in Euclidean space. And here, they meet at a line that's not infinity, and we're still rotating around that line. But so there's some correspondence like that going on here, but I don't think it's as simple as just projectively transforming and then untransforming.
So in particular, the Delaunay triangulation doesn't depend on the angle between the two planes?
That seems to be true.
Even in the Euclidean case?
Well, in the Euclidean case, it doesn't depend on the distance between the two planes, yeah. Okay, I want to talk now about optimal Moebius transformation. This is from a paper that I had with Marshall Byrne at the workshop on algorithms and data structures in '91. So a Moebius transformation, there are a lot of ways to describe them. One of them is that if we think of the set of complex numbers as forming a plane, the a plus bi is the Cartesian point AB. Then if A, B, Z, sorry, I just used A and B as meaning something differently, but if A, B, C, and D are any four complex numbers, then this function mapping z to the point a z plus b divided by cz plus d is another complex number. Or it might be infinite if cz plus d is 0. And that function maps the complex plane to itself in a certain way, and that way is called a Moebius transformation. Or there's a geometric definition that has to do with inversion of circles. And so an inversion is a transformation of the plane to itself, not depending on coordinates, but depending on an input circle that's given to you, and that's this red circle here. And for any other points in the plane, say this green one here at the intersection between these two lines, you map it to another point that's on the same radius of the circle. It's on the ray through the center of the circle and the original point, in such a way that the product of the distance from the center to the original point and to its transformed image, that product of two distances is equal to the radius squared of the circle. So this green point maps to this blue point maps back to the green point, and vice versa. One can do the same thing geometrically. If you have a point inside the circle that you want to map, you can do so by taking a perpendicular to this radius and then finding a circle through the 2 points where it crosses the circle and the center of the circle, and crossing that circle with the radius. You can also do the reverse of these points here. If you started with the blue point and wanted to know where the green point is, you could again find these crossing points here by taking tangents from this blue point to the red circle. So all of this inversion can be constructed with compass and straight edge, and it turns out to have some nice properties. For one thing, circles map to circles. So this triple of dark blue circles on the outside over here maps to this triple of blue circles inside here. It maps the outside of the circle, of the red circle, to the inside and vice versa. Incidences are preserved. Angles between curves are preserved. It's a conformal map. And in order to make it well-defined everywhere, one has to add a single extra point at infinity that is the transformed image of the center of the inversion circle. So that's what an inversion is. And then a Moebius transformation is what you get when you perform a sequence of inversions, or sometimes one only looks at sequences of even numbers of inversions in order to preserve the orientation of the plane. And this, because it's all possible products of a certain kind of geometric transformation, it forms a group, it preserves circles, it contains all transformations that preserve circles. And actually, in dimensions higher than 2, it is the group of all conformal transformations. In dimension 2, that's not true. There are more conformal transformations other than these ones. So it's a very important geometric group. And the problem that I'm looking at is one of picking out from this group of transformations one that optimizes some shape of the input. So we've seen that there's actually been a lot of other work in computational geometry of picking out the translation or the congruence or some member of some group of geometric transformations that, for instance, makes two shapes as similar to each other as possible, and using that to measure similarity between shapes. Here I only have one shape as the input, but I want to transform it in such a way that the transformed shape is somehow optimal according to some measure. And I'll describe what sorts of measures I'm interested in. So this comes up in several different kinds of applications. Well, I've been for many years looking at problems of mesh generation. So we have some input shape that we want to partition into simple regions, such as these sort of rectangular things over here, so that we can apply the finite element method and simulate stress or heat flow or some other physical property of objects made in this shape. And there are different ways of doing this. In this application, what I'm interested in is a mesh that has this very regular grid-like connectivity. And one can do that by finding a conformal map from the object into a grid, using the square grid that grid you've mapped it into has, and then inverting the initial conformal map to take the grid points back to the original shape. Okay? There's sort of a problem of non-uniqueness here. The Riemann mapping theorem says if this is a simply connected region, it always has a conformal map from here to here. But in fact, there's more than one conformal map. And if the central shape was a circle instead of a square, the set of conformal maps can be parameterized by Moebius transformations. So we have a choice to make of which conformal map to make. That choice can be made by specifying a Moebius transformation of a circle to itself. And these different choices will give us different end products, different meshes in the result. Some of these meshes will have smaller elements in some places and larger elements in other places. Others might be more uniform, like this one. And in general, when we're applying the finite element method, sometimes non-uniformity is important. Some areas of our mesh should have small elements. Some areas should have larger elements. And sometimes, so different points of our domain, we might have different requirements for the element size. And we want to find a mesh using this type of transformation that matches as best possible our size requirements. So the problem that we're looking at then is finding a conformal map that such that if we use a grid that's fine enough to match our size requirements everywhere, we minimize the total number of grid elements. And that can be expressed as one of these optimal Moebius transformation problems. Second application, this is sort of blue sky-ish, but this group involving Monica Hurdle, Ken Stevenson, and others have been looking at visualizing the human brain. The human brain is this very complicated, convoluted surface, right? I mean, it's really a three-dimensional object, but all of the important computation happens on its surface. And so you'd like to stretch out the brain into something flat so that you can see as a two-dimensional surface what its functional areas are, how they relate geometrically to each other. And so Hurdle et al. Have been doing this by conformally mapping the surface of the brain onto a nice planar surface. And again, we have this problem that conformal mapping is unique up to some kind of Moebius transformation. Conformal mapping does avoid some kinds of distortion. It avoids distorting angles, but of course the areas can be greatly distorted. We can take a very small area of the brain and it might get blown up into something quite large. And we'd like to minimize that as much as possible. So if you think of the brain that you're given as input to an algorithm, the brain model as being a three-dimensional triangulated surface, you know, in Euclidean geometry, just the surface of your brain divided into lots of little triangles. And some quasi-conformal map from that surface onto a plane, we'd like to Moebius transform that map in such a way that the resulting transformed map minimizes the maximum distortion of any of the triangles. And again, that can be expressed as an optimal Moebius transformation problem. Third application involves graph drawing, graph visualization. There's this famous theorem proven by several different people that any planar graph can be represented by disks on a sphere in such a way that each vertex of the graph corresponds to a disk. Two vertices are connected by an edge if the disks are tangent. And so I've drawn that here in a couple of different ways. So here's our graph. It has 8 vertices. Here's a collection of 8 disks on a sphere that realize that graph. And in fact, we can realize the graph itself as a polyhedron with the vertices of the graph equal to the vertices of the polyhedron in such a way that these disks are the horizons that each vertex sees if it looks at the unit sphere. And these disks actually can be done in such a way that the point of tangency is a point where the edge of the polyhedron just grazes the unit sphere. With a little care to what happens when this isn't the graph of a polyhedron, this representation can be made unique up to a Moebius transformation. Different Moebius transformations of the sphere, of the surface of the sphere, take tangent disks to tangent disks and give you a different looking representation of this graph. And some of them might be easier to look at and understand visually than others. In particular, if we have really tiny circles, it's kind of hard to see what's going on there. We'd prefer a drawing like this one where all the circles are relatively large. And so I'd like to look at the problem of finding the Moebius transformation that transforms the surface of the unit sphere in 3D to itself, maximizing the minimum size of any of these circles. And that is going to give us a nice visualization of the graph, on top of which it's also going to have a further interesting property, which it turns out that the optimal transformation is unique in some sense. And because of that uniqueness, we're going to have the property that when we transform this disk representation to maximize the minimum size of any circle, the transformed representation is also going to be very symmetric. It'll display any symmetries that the initial graph embedding had. So here we started with a graph. There's an obvious symmetry in the drawing of the graph that you can flip it horizontally and get the same graph back again, but there are more symmetries than that. And if you look in the set of spheres over here, each of these 4 small spheres is symmetric to each of the other ones. Each of the 4 large spheres is symmetric to the other ones. And so there's a lot more symmetry that's visible here than here. And that's because of this optimization that we've performed. Yeah?
You said that these transformations don't preserve area. Do they preserve some kind of area monotonicity?
I don't think so. I'm not even really sure what that would mean.
No, but by a Moebius transformation, you can make any of these circles the largest circle.
Right. In particular, you could choose your favorite circle and you could make it into a great circle. So, yeah.
So the objective function you're putting on this is that you want the smallest circle as large as possible.
Right.
There's, of course, other
There are.
similar objective functions one could think of that all would give this uniqueness property, like
Yes.
minimizing the difference between areas of these, or
Right.
basically you have this function of the
There are different objective functions we could choose. I think this is a reasonable choice, but the other reason that I'm making this choice is it's something I can optimize. Okay, so the technique. Before I get to technique, it turns out that Moebius transformations, although I've described them in Euclidean space, actually have a more natural definition hyperbolically. If we want to transform Euclidean space by Moebius transformation, a way that I think works better to think of it is that we view that Euclidean space as the boundary of a half-space model in one more dimension. And the hyperbolic isometries of that d+1 dimensional space are in one-to-one correspondence with the Moebius transformations of the boundary of the hyperbolic space. So this gives us a way of using hyperbolic geometry to describe Moebius transformations. Continuing with that description of Moebius transformations hyperbolically, I talked about the Klein model and the Poincare model as if, you know, every hyperbolic space has one Klein model and one Poincare model, but of course that's not true. The hyperbolic space is completely symmetric. Every point is identical to every other point by some symmetry. Transformed, you know, it's transitive symmetry group. Every direction that you view from a point from is identical to every other direction. And so in the Poincare model, in the model, not in the hyperbolic space itself, but in the model of the space, there's a distinguished point, the point at the center of the circle, center measured Euclideanly. And a distinguished direction if we impose some kind of coordinates on the Euclidean space, for instance, straight downward is a distinguished direction, etc. Okay, so any hyperbolic space has an infinite set of different Poincare models. For every point in the hyperbolic space, one can find a Poincare model that has that point as the center of the unit disk, and looks in. And for every rotation of that Poincare model, you get a different equivalent Poincare model. Okay, so somehow an isometry of hyperbolic space to itself can be viewed as equivalent to a choice out of this infinite family of some particular Poincare model. It's not a very intrinsic way of thinking about hyperbolic isometries, but it's an equivalent way of thinking about them. And so I've said in the previous slide, Moebius transformations can be viewed as equivalent to hyperbolic isometries. Hyperbolic isometries can be viewed as equivalent to choice of a Poincare model, and that choice is factored out into two parts. One is, where's the center of the model? Which point among all these infinitely many points in hyperbolic space is the one that goes to the center of the unit disk? And then, which way do we turn the unit disk after we've picked the center? Now, turning the unit disk is a Euclidean. If we're looking at a Poincare disk model of hyperbolic space, turning the Euclidean disk is a Euclidean rotation. It doesn't affect the shape of things on the boundary of the hyperbolic model. So this part is unimportant for our optimization problems, and this is the part that actually changes what the shape of what we're looking at is. And I've written this here for the Poincare disk model, but very similar considerations apply to the Poincare half-space model, which is what we use if we want to transform Euclidean plane shapes. And then we're going to use a technique that I introduced in a paper with Nina and Marshall called quasi-convex programming that I'll describe for you in the next few slides to find that optimal center point. So back to Euclidean space. A quasi-convex function is one that the level sets, the sets that have function values less than or equal to some particular bound, I guess I should call these downward level sets, are convex sets. So these green triangles are supposed to represent the level sets of some function. The function is large out here and gets smaller within each successive triangle until its minimum is somewhere in here. And the red ellipses represent another of these functions, and the blue squares represent another of these functions. So we want an algorithm that takes as input a set of functions that have this quasi-convex property And we want to minimize the maximum value of this function. So we're trying to overall minimize. This green set of triangles would like our minimum to be as close to this center as possible. The blue set of squares would like our optimal point to be as close to its center as possible, et cetera. And we have to compromise and find a point that's somehow simultaneously small for all of the input functions, so minimize the maximum of these functions. That's a quasi-convex program. We've applied this technique for several other problems that are, as far as I know, have nothing to do with hyperbolic geometry, but it has non-hyperbolic applications. Quasi-convex programming, this formulation, minimizing the maximum of a set of quasi-convex functions, is a special case of an even more general framework for geometric optimization called generalized linear programming that starts from a lot of people, and I apologize, I've probably left out half of the names of the people who've worked on this area, but starts out looking at combinatorial optimization for linear programs. We'd like an algorithm. Most of the linear programming algorithms, with the exception, I guess, of simplex, but the polynomial time provable linear programming algorithms have time bounds where the running time is polynomial, but polynomial in several parameters, including the numerical precision needed to specify the inputs. And we'd like an algorithm that's strongly polynomial that depends only on the number of parameters input to the algorithm. And typical results in this area are if you have a linear program with lots of variables, that should say n constraint LP. Lots of constraints, but only a very small number of variables. We can solve it in linear time. And these linear time algorithms then turn out to generalize to several other problems that are not linear programs, as long as those other problems satisfy some axioms that describe linear programs and these other problems. And quasi-convex programs turn out to satisfy these axioms. So the consequence of this is we get algorithms that can solve quasi-convex programs using a linear number of primitives, linear here in the number of input functions, as long as the dimension of the space in which these functions are defined is bounded. So these algorithms perform a constant number of primitives. Most of the primitives are testing whether a given function value is less than or greater than some amount, and that's easy. But we have to solve a sublinear number of what are called basis change operations, and that involves solving a constant size subproblem. It's not always obvious how to do that. The reason I like this quasi-convex formulation over the general linear programming formulation is that we can also solve them numerically. And because if each of the individual functions is quasi-convex, this objective function maximum of quasi-convex functions is also quasi-convex. And if we have a quasi-convex function that has these nested sets, we can just do some kind of gradient descent search to find the optimum. It's not quite as simple as that because we can get stuck in situations where there's this very narrow canyon that we're trying to traverse down to find the low global minimum. And if we just go out in a random direction, we'll head up one of the walls of the canyon and not make an improvement. So it can be a little bit difficult to find a direction to improve a non-optimal point. But if all of the input functions are nice, smooth functions, what we can do is compute their gradients, find an improvement direction that's inside the convex hull of all the gradients, and that'll give us a global improvement direction. So that's quasi-convex programming, and I've described it Euclideanly, but it just involves straightness and convexity. So it works in hyperbolic space as well if we have a function defined on hyperbolic space that is quasi-convex, meaning that its level sets are convex regions of hyperbolic space. And so if we can specify a way to represent the quality of the Moebius transformation as a maximum of quasi-convex functions where each function argument tells us where the center point of a Poincare model is, then that'll let us solve our problems. The tricky part is actually going through the hyperbolic geometry necessary to prove that these things are convex. I'll just start with the easiest case, which is this coin graph problem. So we want to transform the surface of our Poincare model, the boundary of our model, in such a way as to make these disks big. And if we just look at one individual circle on the boundary of a Poincare model of three-dimensional space, that circle is the boundary of a spherical cap that meets the boundary perpendicularly. So there's a unique hyperbolic plane that goes through that circle. And in order to make the circle big, what we want to do is find a center of a Poincare model of our hyperbolic space where the center is near that plane. It turns out that the radius of the circle is a function only of the hyperbolic distance of the center point of the Poincare model from the plane through the circle. And so the level sets of our objective function then are these sets of points that are within distance k of a hyperbolic plane. Hyperbolic space is a little different from Euclidean space in this respect. The set of points in Euclidean space that are within distance k of a plane is itself bounded by two planes, one on each side of the plane within that distance. In hyperbolic space, the boundary of the set of points within distance k of a plane is not itself a plane, it's a hypersphere. But it turns out that you get these lens-shaped regions, and it's not too hard to show that they're convex. And so we have a quasi-convex function, and we're essentially done. And the same thing works for these other problems. As a result, we can use at least the numerical quasi-convex programming to find these optimal Moebius transformations. It's not entirely clear to me even now whether we can use the strongly polynomial versions, in the sense that one has to compute these optimal solutions of constant size subproblems, and it's messy. At least maybe it's possible always in principle, but working out the actual coordinates of what happens, I don't know how to do very easily. So the numerical one is a lot easier to implement. So I'll stop here. We've talked about computation in hyperbolic spaces. Lots of algorithms translate directly. And in the last two problems, we saw that the hyperbolic viewpoint is useful even if you don't care about hyperbolic geometry for itself, but as a way of solving Euclidean problems. And I think there's a lot more to do in this area. So that's it. Yeah.
What exactly is the uniqueness claim of this optimal Moebius transformation?
Oh, so the uniqueness is just that it's the same sort of uniqueness that linear programs have, that if you make some kind of genericity assumption that there's a, any local optimum is a global optimum.
But in general, the optimal center point is not unique, or is it?
In general, the set of optimal center points is convex. That's what happens. And so you have to go a little step further from that to get to this graph symmetry display property. But yeah. Yeah.
Is the output-sensitive bound of channels non-optimal for output-sensitive algorithms?
Optimal up to polylogarithmic factors. So it's got these two extra logs. Right. I mean, the output is n plus t times log squared. What we would prefer, and what we get in this two-plane case, is n log n plus t. So two differences. One, it has only one log instead of two, but the other is that the log only affects the n and not the t. Yeah.
Maybe I have a comment. The hyperbolic point of view has also been useful in the computation of minimal triangulations, namely, for example, the work of
Oh, okay, that's right. It's not really very algorithmic, but there's this combinatorial geometry question of hypercubes in general dimension if you want to triangulate them. For instance, a three-dimensional cube has two combinatorially distinct triangulations, one with 5 tetrahedra and one with 6. And so we want to know what's the minimum number of triangulations that a cube could have in n dimensions as a function of n. The best lower bounds are
What's the number of triangulations?
no, what is the minimum number of simplices in a triangulation? So the answer for 3 dimensions is 5. There's a triangulation with 5 tetrahedra. And we know the answer for small numbers of dimensions, but as a function of n, we don't know it. The best lower bounds are roughly an exponential factor away from the square root of the factorial. The best upper bounds are an exponential factor away from the factorial itself. So there's a big gap between the two. And I think the best lower bound that's known is that the one by Warren Smith? Involves viewing the cube as a hyperbolic set and looking at hyperbolic volumes of simplices.